Well, how much energy does it require to vaporize, say, some water? This is called the heat of vaporization. It requires heat. You have to put heat into it. So delta H, vap, for vaporization. It's the amount of heat required to vaporize 1 mole of liquid. Because if you vaporize 5 moles of liquid, it's going to take more energy, right? The amount of energy to boil water is greater for a giant pot as opposed to a little tiny pot. So this is the chemical equation for what's going on here. We've got water in the liquid state going to water in the gas state. This is a physical change, isn't it? Because the water molecules have not changed. They're just changing physical state. At 100 degrees Celsius, which is the normal boiling point of water, it requires 40.7 kilojoules of energy to vaporize 1 mole of water. This is a positive number because that energy has to be added to the water. Remember, for energy, we're thinking of the reaction. You put yourself in place of the water. Is energy coming into me? Is money coming into my wallet? This is a positive thing. So energy is coming into the water, and so delta H is positive. If we condense, we said condensation was an exothermic. So this is the opposite reaction. Here we have water in the gas state going to water in the liquid state. Conservation of energy tells us that the amount of energy involved is the same. The sign is different because the energy is moving in a different direction. Now you're taking energy, water in the gas state, and as it condenses, it's losing, it's paying out, giving off 40.7 kilojoules of energy for every mole. So now delta H is negative because this is exothermic. Okay? We can use the heat of vaporization to calculate the amount of energy needed to vaporize a given amount of liquid. It works as a conversion factor between moles of liquid and amount of heat. And so you can look up these heats of vaporization in tables. And so they've given you this table 12.2 in your textbook, and this has 4 different compounds. And it gives the normal boiling point. It gives the heat of vaporization at the boiling point and also at room temperature. The heat of vaporization at room temperature is higher than at the boiling point, which makes sense because it's going to require more energy to vaporize if it's not as warm. So the heats of vaporization can vary quite a bit. We can look at the heat of vaporization and get some clue about the strength of the intermolecular forces. Water has a heat of vaporization of 40.7, and down here diethyl ether is only 26.5. This requires less energy to vaporize. So that tells us that the red rover line is weaker. It doesn't take as much energy to break through, and so the heat of vaporization is lower. Let's calculate the amount of heat required to vaporize 25 grams of water at its boiling point. And they're telling us the heat of vaporization is 40.7 kilojoules per mole. Well, let's try to organize this information. So here we've got 25.0 grams of water, and then we're given this 40.7 kilojoules per mole. It's written with a slash here because that's easier to type, but when you write it on your paper, write it as a vertical fraction so you recognize that it's a fraction. So what we've learned is that, when we're trying to decipher a word problem, look at the numbers. Here we're given 2 numbers, and so you have to decide, well, what number am I going to start with? This one just has a single unit, grams, and this one has something per something. This is the conversion factor. This is what we're starting with. And what are we trying to find? What's it asking for? Amount of heat. Heat is energy. What's a unit of heat? Kilojoules. It doesn't specifically say kilojoules, but we've got this guy over here, and that's got kilojoules in it, and so we could get to kilojoules pretty easily. This relates kilojoules and moles. So if we knew how many moles of water, we could use that to convert to the amount of heat. Can we go from grams to moles? Yeah, we learned to do that a while ago. So this is our path. This just comes down to being a unit conversion problem. So 25.0 grams of water times in a line times in a line. The units, grams to moles to kilojoules. So grams to moles to kilojoules. I'm going to take this unit and put it in the denominator, because I want those to cancel out. And then I'm going to take moles and put it in the denominator, because I want those to cancel out. Get all the units in place first, and then put in numbers. Well, this one was given to us, so that's easy. 40.7 kilojoules per mole. I want to keep 40.7 and kilojoules together. You can't swap them around. And how do I get the relationship between grams and moles? What do I need to look at to find that? I need the periodic table, right? And the formula. We've got 2 hydrogens and 1 oxygen. So 2 times the mass of hydrogen from the periodic table plus the mass of oxygen. And that comes out to 18.02 grams per mole. So that's 1 mole is equal to 18.02 grams. (25) divided by 18.02 times 40.7. The smallest number of significant figures in there is 3, so I'm going to round my answer to 3, 56.5 kilojoules. That's the amount of energy needed to vaporize 25 grams of water. Any questions? Let's do another example. A drop of water weighing 0.48 grams condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? The specific heat capacity of aluminum is 0.903 joules per gram degree Celsius. Anybody want to say, ah? What? Numbers, words all over the place. It's okay, we can do this. Sometimes it helps to draw a picture. So this is a block of aluminum. Aluminum is kind of a silvery metal, right? So I'm going to draw a block of aluminum here. That's my aluminum. What do we know about that aluminum? It weighs 55 grams, right? What else do we know about it? We know a temperature. So 25 degrees Celsius. And then there's this drop of water. Water is blue. So here's the drop of water coming down. What do we know about the drop of water? 0.48 grams, right? And it's condensing. It's kind of hard to write. Well, that's about all we know about the water. What's this number? What's this 0.903? Does that refer to the aluminum or to the water? Aluminum. So we kind of missed that one the first time, so let's write that over here. 903 joules per gram degrees Celsius. So this water is condensing. It was in the gas state and it's condensing to the liquid state. Is that going to absorb energy or release energy? It's going to release energy. Where is the energy going? To the block of metal. It says right here, if the heat released during condensation goes only toward heating the block of metal, it's asking for a final temperature. So this temperature, which, wow, that's really messy, isn't it? Let's see if I can fix that. 25. Is that a final temperature or an initial temperature? That's an initial temperature. And 55 grams is what? Grams measures mass. And that kind of looks like specific heat capacity, right? Do you remember MCAT? So Q equals MC delta T. Here we've got an initial temperature. We're trying to find the final temperature. We've got a mass. We've got C. That's what this is. The specific heat capacity is C. But we don't know what Q is, do we? Where is the heat coming from? The water condensing, right? It's not given in the problem, but how much energy is released when water condenses? We just used this number. I happen to remember it. 40.7 kilojoules per mole. With these two numbers, could we figure out how much energy is released? Yeah, we could. Well, let's do it. So we're going to take, I'm going to go with a lighter blue so it's a little easier to see. 0.48 grams. This is the same calculation we just did. We're going to convert to moles. We just used this molar mass of water. And then we're going to find out that that's 40.7 kilojoules per mole. .48 divided by 18.02 times 40.7. So 1.084 kilojoules. That should have two significant figures, but I'm going to keep the 8 and the 4 because I don't want to round it off because I'm not done yet. That's the amount of heat. That's Q. Now I have Q, and I have C and M. I could find delta T. So that's what I need to do. I need to take this equation and solve for delta T. Delta T equals Q divided by MC. So now I'm going to put in Q, 1.084 kilojoules. That's divided by the mass, 55 grams, times the specific heat capacity, 0.903 joules per gram degrees Celsius. Grams cancel out. Do kilojoules and joules cancel out? No, they don't. So what I'm going to do is I'm going to replace kilo with what kilo means. What does kilo mean? 10 to the third joules. Now the joules cancel out. .084 times 10 to the third divided by 55 divided by 0.903 equals, the temperature change is going to be 21.8 degrees Celsius. So I know the initial temperature, and this is the temperature change. Is the temperature change positive or negative? Positive, meaning it's going up, right? So final temperature is going to equal the initial temperature plus the change in temperature. It's 25 plus 21.8, which gives us, what, 47 degrees Celsius. Any questions?